Hey, good morning everyone. Today we are going to study our experiment number 3, which is about the study of or use of external interrupts with 8051, right? So although you have studied very well about the interrupts in your classrooms, let us have a brief review about the interrupts, different types of interrupts, and what actually happens when the interrupts actually occur, right? So what is an interrupt? So what is an interrupt? Interrupt is a signal generated by an event that causes the controller to stop temporarily its current program execution activities and perform the task to service that event, which simply means that suppose your microcontroller is performing a task right now and an interrupt occurs. So whenever an interrupt will occur, so what will happen? Your microcontroller will suspend the execution of the program which is executing right now and provide service to the interrupt. Once that service is completed, it will come back again and resumes the execution of the program which was suspended. Now the point comes why the interrupts are required. Suppose there are some important events which are happening which microcontroller is unaware of. So let them inform about that thing. To inform the microcontroller about the events which are happening, we can use our interrupts, right? Means to grab the attention of the microcontroller, we can use the concept of interrupt. Means interrupts are used to get controller attention towards important events or activities. Is it clear? And remember, normally your interrupts are asynchronous. Keep that in mind. They are asynchronous. So whenever asynchronous activity is occurring and we want to inform our microcontroller about the same, we will use the concept of interrupts. Now move ahead. Why do we require interrupts? As we know, our if we talk about laptop or we talk about desktop or we talk about any smart system, it has lots of peripherals which are attached to it. And suppose any peripheral requires a service. Okay, so how will the microcontroller aware that this particular peripheral require my service? One way is to use the concept of polling, right? What in the polling will happen? Your microcontroller will continuously monitor the status of peripheral. It will continuously monitor the status of peripheral, but while it is doing same, it cannot perform other tasks because it is continuously monitoring, means its time is getting wasted. It may be possible that peripheral is not requiring any request or any service from the microcontroller. He is not wanting any attention from the microcontroller, but the task has been assigned to the microcontroller. You have to continuously monitor that my peripheral requires service or not. So unnecessary time wastage, power wastage is happening in the concept of polling. So what is the better option of that? The better option is interrupt. In interrupt, where it will happen, instead of continuously monitoring the peripheral, my microcontroller will keep on working its normal operation, and whenever any device requires attention or services of the microcontroller, it will send an interrupt signal to the microcontroller. Is it fine? That's why interrupts are way better to handle the request from peripherals. Okay, moving ahead. There are normally how many types of interrupts in 8051? So there are generally 5 kind of interrupts. They may occur internally or externally. If we talk about internally, there are 3 interrupts known as timer 0 interrupt, timer 1 interrupt, serial port interrupt. And if we talk about the external interrupt, there are 2 kinds of interrupts: external interrupt 0 and external interrupt 1. Okay, so let's get a concept of what happens. Suppose there is an event occurs outside and my peripheral wants to inform my microcontroller that event has occurred, and he sends that signal on external interrupt pin INT0. So as soon as my microcontroller will receive this external interrupt, so what will happen? Think everything properly, right? So it will suspend the execution of the current program and provide service to the external interrupt 0. Now what task has to be done? Now keep that in mind. Whenever a microcontroller is providing service to the interrupt, it needs to perform certain tasks which a peripheral is demanding or anything else is demanding which is generating the interrupt. For example, I was saying the interrupt is being generated at INT0. So what will happen? As soon as the interrupt occurs, the microcontroller will suspend the execution of the current program and go to the vector address of the corresponding interrupt. Okay, so whenever interrupt will occur at INT0, the microcontroller will suspend the execution of the current program and will go to the interrupt vector address of external interrupt 0. And at this address, what task has to be done by the microcontroller? What task has to be done by the microcontroller to provide service to this external interrupt 0 is written. Means what task is written will be starting from this address, interrupt vector address. And the task that it will perform will be known as normally interrupt service routine. Okay, so I'm repeating once again. Suppose my microcontroller is performing certain operation and there is an event or there is an interrupt at external interrupt 0, INT0. So microcontroller will stop the execution of the current program and will go to the interrupt vector address, which is 0003H, and here our ISR is stored, that is interrupt service routine. So that interrupt service routine will be executed by the microcontroller, and once that get executed, it will return back to its main program which it was executing earlier, right? So what essence is that at the interrupt vector address, the address of ISR, where our ISR is actually stored in the memory, is there. For example, INT0 bar has interrupt vector of 003H, TF0 has 00BH. So every interrupt has a particular interrupt vector address where the corresponding interrupt service routine is stored. Okay, now move ahead. To make use of interrupts, we need to use basically two registers, which is interrupt enable register and second one is interrupt priority register. So let us understand first of all about the interrupt enable register. Suppose you want to enable the operation of interrupt, means you want someone to interrupt you, or you want to get aware whenever, means that you want that peripheral should inform whenever they require my service. For that, it has a 8-bit register known as interrupt enable register. We have to configure it, right? For any interrupt to work, first of all, you have to enable this EA pin. This is known as global enable pin, global enable bit. If this bit is 1, it allows each interrupt to be individually enabled or disabled. Okay, if EA is 1, that means it allows each interrupt to be individually enabled or disabled. But if you make it 0, it will disable all the interrupts. Getting my point? If this bit is 0, means interrupt makes no sense, all enables or interrupts are disabled. But if you want the functionality of the interrupts, you have to first enable this EA pin, and after enabling this pin, whatever interrupt you want to be enabled, you can make that corresponding bit to be 1, and if you don't want that interrupt to be enabled or you want it to be disabled, make that corresponding bit to be 0, right? So this is the EA pin. This bit is reserved for the future purposes. This is enable bit for timer 2. This is enable bit for your serial port. This is enable bit for timer 1. Enable bit for external interrupt 1. Enable bit for timer 0. Enable bit for external interrupt 0. So whichever interrupt you want. For example, I want external interrupt 1. So I'll make it 0. And let us take an example. Here I want to enable external interrupt 1. This interrupt I'm talking about. Disable all rest of the interrupts. So what I will do, I will mark EA to be 1 first of all, because I want to enable one of these interrupts. So I will mark EA to 1, EX1 to be 1, because I want to enable this interrupt, and rest to be 0, right? So what will happen, you can see over here, this bit will be 1, these will be 0, this will be 0, this will be 0. This will be 0, this will be 1, this will be 0, this will be 0. So whatever structure of this register will be 0, 0, 0, 1, 0, 0, 0, 0, 1. Okay, I'm repeating again. If we go from here, 0, 0, 1, 0, 0, 0, 0, 1 in binary. If you combine them in a hexadecimal, so what will happen if we talk about the lower nibble, it is 0, 0, 1, 0. So it will become 4. This 4 nibble will make a, so nibble means combination of 4 bits will make a, in hexadecimal, 4. And this 0, 0, 0, 1 will make it 8. Okay. So if we talk about, if we want to enable our external interrupt 1, so what we have to do, we need to configure enable register in binary to be 1, 0, 0, 0. 0, 1, 0, 0, and in hexadecimal it needs to be 84. Okay, this way you can enable your register. Now There are lots of interrupts. We can see there are 5 interrupts, right? By default, if we talk about the interrupts, the highest priority is given to the interrupt at pin number 0. Right? Highest priority is given to the interrupt pin number 0, that is INT0. And the lowest priority is given to the serial port interrupt. Remember again, INT0 has given the highest priority and serial port has given the lowest priority. But if you want to change the priority, you can use another register known as interrupt priority register. Okay, where you can set the priority of individual interrupt by making it 1 or 0. Getting my point? So if you set that particular bit to be 1, it is set to be higher priority. If you set that particular bit to be 0, it is set to be lower priority. Getting my point? So by setting any of these pin as 1 or 0, we can make their priority to be high or low. For example, I make PX0 means 1, which means that this interrupt will have a higher priority. If I make it to be 0, that means this interrupt will have the lower priority, and same can be applicable for all the interrupts which are available. Is it clear? Fine. This is for timer 2, this is for serial port, this is for timer 1, this is external interrupt 1, this is for timer 0, this is for external interrupt 0. For any of these you can set the priority high or low. I repeat again, if this particular bit is set to be 1, it has a higher priority, and that particular bit is set to be 0, it has a lower priority. Okay. Now one more thing. Suppose we are talking about the external interrupts, right? So those external interrupt can be level triggered or edge triggered. I repeat again, those external interrupts can be level triggered or edge triggered, and for that we have a particular bits in our timer control register known as TCON, right? By enabling the TCON bits, if you enable those TCON bits to be 1, those become edge triggered, and if we disable those TCON corresponding bits, those become level triggered. I repeat again, for external interrupts there can be option of level triggered or there can be option of edge triggered interrupts. This can be controlled by using the TCON bits of the timer control register. Okay, so how do we normally generate edge triggering or the level triggering? Level means simply we can connect it here. For example, this is 5. We can easily connect it as a level trigger. If you want to know about the edge triggering, so what can do? I have tried to construct a circuit here. It is an interrupt 1 I am using, which is the pin number 3 of port number 3, means bit number 3 of the port number 3 that we are talking here, right? This is the one which is available here. I want to make it as an edge trigger, right? So I will do that by the help of software in the TCON. But here what I can do, I have pulled this pin to VCC. I pulled this pin to the VCC and connected one switch over here. What happened when this switch is in off condition, when there is no connection between ground and this pin, it will be connected to the 1. It will be connected to the 1, and once I push it down, I push the switch down, this particular pin is connected to the ground, means from high to low it goes, and this is the negative edge trigger. Okay, this way we can generate the negative edge. I repeat once again, I pull this particular pin to the VCC, and in the absence of connection of this switch, this particular pin will be receiving 1, and once I push this switch here, then what will happen? This ground will be connected to this pin and my interrupt will receive 0. But now what has happened? The negative edge has happened, because earlier it was 1 and now it has gone to the 0. So now negative edge has occurred. Okay, now let us say our task is to count the number of interrupt which has occurred. Number of negative edge triggered interrupt has occurred at the pin number INT1 that we are talking. Okay, we want to know how many times the interrupt has occurred at this particular interrupt. Okay, this is our task. So what our task is, write an assembly language program to count the number of times an external interrupt occurred. Okay, here as you can see, and also send the count on port 2. Also send the count on port 2. Remember what we have to do. Remember that thing. What are the tasks? List out every task that you have to perform. Okay? So what we require basically 2 programs. One program is your main program and second program is your service routine, interrupt service routine. Remember that thing, and that particular service routine will be stored at particular vector address of corresponding interrupt. Okay, and as we have been asked to add interrupt 1 bar, let us go back and check it out. What are its vector address? Let's go here. Okay, you can see that external interrupt 1, that is interrupt 1 bar, has a vector address of 0013h. So at this particular address, our interrupt service routine or what task has to be accomplished when an interrupt occurs has been should be stored. Okay, 0013h. So what we did, see, very simple things are there. We write the memory address where our program should start, org000h. I press long jump main, means normal operation, jump to the main operation, and here main, our code is code as this particular address, that is 0030h, where the program is move R000h. I use a register where I have put the value 0. Okay, I've used a register where I put the value 0. Now what I did, remember, first of all, to enable any interrupt, you need IE register, interrupt enable register, to be configured. But for that, you remember, EA bit has to be set 1 and corresponding interrupt bit has to be set 1. And we have already seen that. If you remember, we are talking about interrupt 1. Let's go back. Let's go back a bit. Here, this bit has to be enabled, and interrupt external 1 they are talking. So this bit has to be enabled. Rest of the bit has to be 0. So it becomes 0010 0001. Right? Means if we read from this way, from MSB to LSB, it will be 10000100. And if we group them in hexadecimal, that means 0010 will be 4 and 0001 will be 8. So in hexadecimal it becomes 84. Okay, remember that thing. So what we are doing, we are storing, or we are saving 00 in R0 register. That means it's a hexadecimal data, so our entire bit of R0 will consist of 000000 only. Now what happens is that we initialize our IE, or we enable our interrupt enable register. Okay, we set our interrupt enable register as per our requirement. So what we write, move IE #84h. Okay, so what, after writing this command, what is happening, your interrupt enable register has been your interrupt has been enabled, and for what particular interrupt is enabled, your particular interrupt at interrupt 1 is being enabled. Okay, after that, remember I told you it's up to you what you want. You want it to be level triggered, you want it to be age triggered. As we are using this to be age triggered, I told you earlier there is a particular bit in TCON or timer control register. For this case is a bit number 2 for INT1, right? So what happens, we need to set it 1. So I write set B TCON 0.2, means 0.2 means bit number 2 of the TCON register. Starts from 0, 1, 2. So it's a bit number 2 of TCON register, set it to be 1. Once we set it to be 1, that means it has become now negative age triggered. It has become now negative age triggered. Okay, and after setting this, I just write here S jump here, means wait here till the interrupt occurs. Wait here till the interrupt occurs. And when the interrupt occurs, what happens? Whenever interrupt will occur, you will go to the interrupt vector address. And what is the interrupt vector address? Remember, for this case it was 0013h. For interrupt 1 it was 0013h, where now what you want, whatever task was, whenever interrupt occurs, okay, we have to count that how many times the interrupt has occurred, right, and send the same information to the port number 2. So what we did, if we are moving here, means after this interrupt has occurred, immediately jump to this address where what is happening, where our ISR is stored, interrupt service routine, and here what is written, increment R0. So first time we are coming here, it will increment our R0. R0 was initially what, 0000. So once we will increment it, it will become 1. Okay, it will become 1. Now our task was to send it to port 2, and by default, if you remember, except port 0, all the ports 1, 2 and 3 are pulled up. Okay, and as by to visualize that we are able to get how many times the interrupt has occurred. We will connect LEDs at the port 2. That means we will connect the output devices at the port 2. We will configure port 2 be an output port, and that's what we have done in the move P2 00H command, because we know if a particular bit is set to 1, that means input port, and if that particular bit is configured to be 0, that becomes an output port. Because we want to drive LEDs, we want to configure port 2 be as a output port, so we are sending 00H at the port 2. Okay, and after that, what is happening, it is configured at the output as an output. We send the value of R0 to the port 2. We send the that to the port 2, and after that we write the return instruction. Return from the interrupt means your service routine is completed. You can go back to your main program execution, and after that last you have the program ended. Hope things are clear what you need to do. Now let's implement the same program in our multisim. I'll copy the same program in our multisim and let's see what happens now. You can see here I've connected few probes here working as LED, basically indicating only. So I've connected LEDs here on the port number 2, get an output, right? And I have connected created a same circuit of the age triggering. I'm connected to the interrupt 1 in number 13. You can see here it is connected to there. You can see here. Okay, so when I will press this switch here, it will connect to the ground. That means a negative age will trigger, and when I will disconnect it, what will happen? It will be connected to the 1. So by default it is connected to the 1. So when I press it, the negative age being triggered. So what should happen? In beginning these all should be 0. In beginning these all should be 0, and when I press this first time, okay, so negative age triggered, it should become 1. When I press it again, I open it, and when I press it again, because I negative age I want, and age will occur when I'll move from this position to this position, remember, right? So when I will press first time, I should get 1. When I press second times, I should get 2, and corresponding. Okay, we can check our assembly code here. This is our assembly code. Same code has been written here that we just encountered earlier. So let's build it. So I'm going to the MCU and building it. As we can see, there's 0 error, 0 warning. So now we can go to our this circuit and let's simulate it. Let's turn it up so that it is by default pulled up. Let's run it. Okay, by default, let's see. I'm pressing it first time. Okay, so only this LED should glow, rest of them should become 0. Okay, this should glow and rest of them become 0. So it will indicate only 1. I'm pressing it. Let's see what happens. You can check it out. What happened? First time interrupt has occurred. Let's press 2. Now this bit should become 1. This should become 0 because in binary it will become 2 now. Press it. We get 2. 2 times interrupt has occurred. Move it again. Press it once again. These both should become 1 because it will become 3 in binary. Agree? 3 interrupts has occurred. Now 4. Now what will happen? We'll move to this bit. We'll move to this bit, right? So this should become 1 and this should become 0. So it will become 4. Let's do that. You can see that. Move again. You should get 5. 5 means 101. This way. Getting point? Next move 6. 6 means 110. Get it? Let's move to 7. All 3 win. Now move to the 8. Okay, so our program is working fine. So we have easily studied. This way you can use interrupt 1 or interrupt 0. Any interrupt you can use. It's up to you. Any hardware interrupt you want, you can use it. Any hardware external interrupt you want, you can use it. And whatever task you want to perform, that you have to write in the vector address of your interrupt service routine. Here the tasks are different. You can use the task of generating a square wave whenever an interrupt occurs, or any other task you can do. Hope things are clear to you. Thank you.